Okay, so having a look at this lifting system used to transport engine parts. So we have the drum, which is lowering a load through a cable at a constant acceleration downwards. So what I've done to begin with is I've drawn the diagram in two separate parts. I'm looking at the forces acting on the load from the load's perspective, and then the force acting on the drum. So from the load's perspective, we have the tension in the cable, which is acting upwards, and then we have the load's weight acting downwards. I have to say we are assuming, it doesn't say in the question, but we are assuming that the cable is light and therefore doesn't have a mass and therefore doesn't have any weight contributing towards these force diagrams. The second diagram, we have obviously the drum, and we have the tension acting downwards in the opposite direction towards where the load is. So the drum feels the effects of the load being lowered. So we have the radius of the drum, 0.3 meters. We're told the diameter is 0.6, so I've labeled that. And we've got constant acceleration acting downwards. So looking at the information that we've been given, we have got, well, first and foremost, the fact that we're dealing with constant acceleration means that immediately we should be thinking of the Suvat formula, which can only be applied if we have constant acceleration. So we've got our 5 different kinematic values. In the case we're dealing with here, the load is being lowered down to the ground. It's covered a distance, which or displacement, which S is representing, are 0.4 meters. Initially, it's traveling at 0 meters per second. And we are told the time that has passed is capital A seconds. So it seems like we're going to be dealing with all our answers in terms of capital A. Time is often a kinematic value which overlaps so many different areas of mechanical mathematics. So in our case here, capital A, the time to descend, we're going to see that cropping up in quite a few of our answers. The question doesn't state that all the answers are in terms of capital A, but from my perspective, there doesn't seem to be enough information to be able to gauge exactly what capital A is going to be. So we're going to be seeing capital A a lot. If we have a look at the very first question, we need to find the final linear velocity of the load. So final velocity in the Suvat equations is represented by V. So I want to work out what V is. Given the information that we have, we've got S, U, and we have to consider T being something that we're given as well. We have to consider what formula involves V, S, U, and T. Remember, we're not given A, we're told that A is constant, acceleration is constant, but we don't know what that value is. So I'm going to omit that for now, otherwise we're going to have a little a involved along with capital A. But we're going to stick with these values. So V, S, U, and T, the formula links all those together. There's a few different ways of writing this formula. S equals a half of U plus V multiplied by T. So we can substitute all the information in and rearrange, and we should end up with an expression for V. I'm not going to give it away, I'm going to allow you to work through that yourself. Now let's say I wanted to consider the dimensional analysis technique, just show that the values are homogeneous. So what that means is within our formula, we need to show that the units are consistent using the technique of dimensional analysis. Now, the dimensions that we deal with in mechanics are capital M for mass, capital L for length, and capital T to represent time. So the formula that we've used is this one here, or will be using. So I'm going to show that this formula is dimensionally consistent. In other words, the units are consistent on both sides using dimensional analysis. So if we consider these two sides of the formula, so we've got a left-hand side represented by S, our displacement, and a right-hand side which is a little bit more complicated. So considering the dimensional analysis of this formula, so if we have a look at the left-hand side, represented by S, so that is simply displacement. Displacement is representative of a length. So the dimension we have on the left-hand side is simply capital L. A little bit more work is going to be needed for the right-hand side. So looking at what we have involved here, so we've got two velocities, and we've got a half, which is dimensionless because it's just a value, and we have time t. So mentioned a half is dimensionless, so we're not going to have anything representing the half. So we're going to jump straight to where the units are going to be involved. So U, V, and T. So U and V have units of meters per second. If we consider the dimensions of meters per second, meters is represented by the dimension of length. Per second, so per second of time, so that is per unit of the dimension time. So we can either write that as t to the minus 1, or we can write that as L over t, completely up to you. We're then adding the second velocity. So second velocity will have exactly the same dimensions, so L t to the minus 1, and then t on the outside represented by the dimension of time. Adding these two dimensions together, we're going to end up with 2lt to the minus 1. 2 is dimensionless, so we can ignore that. So we just end up with a dimension of lt to the minus 1. And multiplying this by t, t to the minus 1 times t is the same as t divided by t, which cancel one another out, will give you 1, 1 being dimensionless. And that gives you a final dimension of L. And if you consider what we had on the left-hand side, which was the dimension of L, what we end up with are units that are dimensionally consistent. And I'm not going to go through the dimensional analysis for every single question, but it's this approach that we're looking at to show that all values and units used are homogeneous. Okay, having a look at question B, find the linear acceleration of the load. So this is where we need to work out a value for A representing the acceleration. Now, A is part of the SUVAT formula, so we could basically just use what we've got up here, but this time using a different formula instead of V, incorporating lowercase a. So we've got a choice really of formula because we will have an expression for V up here. So V could be part of the formula if we really want, but just using the ones that we've got up here. So we need to work out what A is. We have S, we have U, we have T. So the formula that links all those together would be S equals UT plus half AT squared. Work through all of that, and we are looking for an expression for lowercase a. And once again, because time is involved, that means we're going to have an answer in terms of the constant capital A. So we'd end up with the result for that. And we'd need to show that the units are consistent. So dimensional analysis, exactly the same technique as above, but implemented on the formula that we used here for SUVAT. Right, having a look at part C. Part C, find the angular velocity of the drum. So when you consider angular velocity, circular motion, angular velocity not to be confused with linear velocity. Angular velocity is the rotation based on the number of radians per second that the object is rotating. Linear velocity would be the speed in meters per second a particular point or an object moving on a circular path is moving. Now linear velocity is represented by v in circular motion. And angular velocity, often represented by omega. Units tend to be meters per second for linear velocity. Angular velocity has units of radians per second. And the link between linear velocity and angular velocity in circular motion is that the linear velocity is equal to the angular velocity multiplied by the radius of the circle in which the motion is taking place. In part A, we actually worked out a value for v, an expression for v rather, in linear velocity, and we know what the radius of the drum is, so in order to work out angular velocity we just need to do a little rearrangement with our expressions, and that will allow us to arrive at an expression for omega, which is angular velocity. I'll leave that with you. Part D. Angular acceleration of the drum. Now, this is quite tricky to work out unless you're either given a formula with how the angular velocity is affected by time. So if you have a function in terms of time, then we can work out angular acceleration through calculus. What I'm going to do, however, although whether this is what you need to work out or not, I'm unsure, but the easiest thing that we can calculate is average angular acceleration. Now, it doesn't say average angular acceleration, so this may be incorrect, but this is quite a straightforward thing that we can work out based on what we've already got, because average angular acceleration is the change in angular velocity, so the change in omega, over the change in time that occurs. Now, the angular velocity, how much the drum is spinning, we know how much that's going to vary to and from. Given that our load starts off at a speed of 0 meters per second, that means that the drum will be rotating at 0 radians per second. So we've gone from 0 radians per second to the expression that we have up here, which is our final angular velocity in radians per second. So if I just call this omega 1, then the expression for change in angular velocity will be whatever omega 1 is, subtract what the initial angular velocity was. And for us, the initial angular velocity is 0. Change in time, so the amount of time that has transpired is represented by capital A. And so very quickly we can work out what the average angular acceleration is going to be using our previous expression for angular velocity. Part E, the tension force in the cable. So if we consider the diagram for the load, so looking at this diagram here, if we consider the forces that are acting and the fact that there's an acceleration taking place, that means that the law F equals ma, or F net equals ma, must be abided by. So F net represents the difference in the forces, so the resultant force taking place in the direction of motion or direction of acceleration. A is simply A, our acceleration, and M being the mass of our load, which is 2 kilograms, not 2g, that's the weight. The mass would just be 2. So F net equals ma is the formula we're going to be using here. Now, our load was accelerating downwards, so downwards would be our positive direction for our forces, upwards would be our negative direction. So our resultant force, our net force, will be the 2g acting downwards for weight, subtract the tension acting upwards. The mass of our load is 2 kilograms. The acceleration A I'm just going to put as A for now, but we actually have an expression for our linear acceleration, which was in part B. So we could rearrange, substitute our expression for acceleration, and we can end up with an expression for capital T, representing the tension force in the gale. And finally, part F, the torque applied to the drum. Well, torque is another way of saying moment, or the moment of force is acting about circular motion. And that takes place on our drum. And if we consider our drum, I won't turn over, just a very quick picture. The torque, or the moment, is calculated by the force that's acting, that's creating the turn in motion, multiplied by the perpendicular distance from our fixed pivot point. Now, for our drum, our fixed pivot point is the centre, which is a distance of 0.3 away from the force that's acting. They're perpendicular to one another, which is excellent. It means that we don't have to overcomplicate things. And therefore, our torque is calculated by, as I mentioned, it's the force multiplied by a perpendicular distance. So this is just symbol I use to say that they're perpendicular to one another. For us, our force that's acting, that's creating the turning motion of our drum, is T, and the distance, perpendicular distance in which the tension is acting, is 0.3. T is something we worked out, hopefully, in the previous question, part E, so we can substitute that in there, and that should allow us to arrive at an expression for torque. Now remember, dimensional analysis needs to apply to every single formula that will have been used to get to our results. And the final question, hopefully once you work through this, it should give you a bit of confidence to be able to have a little think about where the equation of power is deduced. To help you out, power is measured in watts. It can also be measured in another way, but I'm going to allow you to look that up. And you can use dimensional analysis to say, well, the dimensions of power has got to be this, therefore I need an expression that's also has dimensions equivalent to that. So you can start to derive your own formula based on those. And it says that there are two equations for power which can be deduced based on everything that we've got here. So have a little play with that and see how you get on.